Hello everyone, here we are, the Eclipse team. It's me, Mohammed Lutfi Hamad, a member of the Eclipse team. The other members are Ahmed Abdel Sattar, the team leader, Mahmoud Al-Dusui, Mohammed Saeed Salama, and Ahmed Basiri. We are a team of many teams which will introduce their project in the course Digital System Design. Our project is called the Eclipse Clock. The Eclipse Clock is a project that aims to show the digital a digital clock on a 7-segment which is put on a working fan or a rotating fan using the persistence of vision theory. This theory states simply that when we display several frames for the naked eye with a frame rate more than 40 frames per second, the eye will see these several frames as they are one still image. Okay? The persistent vision is still accepted term for this phenomenon in the realm of cinema history and theory. In the early days of film innovation, it was scientifically determined that a frame rate of a calculated range causes the eyes to see the flashing image, which means that if something appears in the same spot consistently, at least 50 or 60 times per second, our brain thinks that it is permanently there when it is really not. TVs and monitors use this method of display, so it is not as uncommon as you might think. To see this theory clearly, you can make a cord and pass it through a paper, a circular paper, which has two faces. One face has a picture of a cage and the other face has a picture of a bird. When I hold this cord and move it circularly with a specific speed, the one in front of me will see the picture as if the bird is inside the cage. As we said, TVs and monitors use this method of display. So we illustrated this project using this theory by using a 7-segment on a fan wing and manipulating them on and off using the Altera board. The Altera board of type DE2 115, and it is clock of 50 MHz. The speed of the fan or the ability of the motor also plays a huge role in manipulating the persistent of vision phenomena and also helps to produce the final output which we require.
Thank you. So it wasn't easy. Actually, we faced lots of problems. But the first and main problem that faced us was how could we connect the static ultra bands and wires with the fast and rotating fan wings, which the 7 signals is connected on it. So after searching and looking around, we find that there is very easy and direct way to do this. And it was by using the slip rings. For those who don't know the slip rings, it's like two plastic cups which are connected and attached to each other, but one of them is rotating and the other is not. And this allows the transmission of electric energy through a rotating substance to another static object. But after searching and going to there and there, we didn't find it in Egypt, unfortunately. So we didn't have any choice but to build something in our own. Our aim and first thought was to create something like the brushes, and these brushes would be used to transmit electric energy to the axis of the motor while the full cycle rotation is going on. And from there, and through a hollow space in this cylinder, in the center of this cylinder, it will be connected to the 7 segments. And by this, we will be connected the static Altera bands output to the dynamic and very fast 7 segments. Thank you.
To illustrate and simplify more what my colleague just said, we will classify the hardware into 3 main parts. The first part is the hollow rotating coil cylinder, and the second part is the arm brush, the third part is the 2 wings. Let's start with the first part. We've designed the first part, the hollow rotating cylinder, to have 10 grooved segments. Each segment have a conductive wire rotating around it and reaching all the way to the segment of the 7th segment. This happens through a hole in each segment that passes the wire rotating around it to the segment on the 7th segment that it wants to control. The second part is the arm brush that consists of 10 brushes. Each brush is connected to a corresponding segment in the hollow cylindrical, and the other end of the wire is connected to the pins of the Altera board, which makes us reach the goal to pass the signal from the Altera all the way to the brushes, which is connected to the grooved segment that passes the current through the hollow cylinder all the way to the segment that we want to control. Both of these parts are made of Artilon material, which is known to be isolator, light and stronger. And the most important thing that it's light, that helps us to control and keep our high RPM, and does not reduce the torque of the fan motor. The third part is the small part with the two wings. The first wing consists of the segment that we have used. As it has, we have used only one segment. The other wing is only used to balance between the two segments to have the
target
same.
was to find a proper motor with high enough RPM that will help us to reach our BOV phenomenon. In this point, we faced two major problems. First problem was that the RPM that was written in the motor we got was not accurate enough for us to make the right calculation for controlling the 7 segments using the Altera clock to display the static state of the clock. The second problem was that the RPM of this motor is not steady, with an average of plus or minus 10% of efficiency, which makes us unable to make the right calculation for controlling the 7th segment within the Altera clock. Our approach for this problem was at first that we tried different types of motors. The first motor was a 9-volt DC motor with a 2400 RPM. The motor torque was very weak, that we couldn't handle the weight of the rotating cylinder and the fan wings, which was only made from styrofoam. The second motor was a 12-volt DC CPU fan motor with a 3500 RPMs. We chose the motor because this was the highest RPM we can get from our local market. Unfortunately, we have faced the same torque problem as the first motor. So we had to change approach and use an AC motors. The third motor was a 220 volts AC refrigerator compressor motor with 1400 RPMs. After reaching our final stages with this motor in the hardware section, we found out that this motor has an extremely inaccurate RPM, and it has different phases and different speeds, and it translates from one state to another automatically, which ruins all of our calculations. The fourth and last motor is a 220 volts AC household stand fan, which we can see here, with 1200 RPMs. The RPM of this fan was not the record one, but we managed to reach our final stage with our right calculations with trial and error. We finally managed and reached that required output by manipulating calculation in the Altera 50 MHz clock.
As my colleagues just illustrated, that we had a problem with the RPM ability of the motor. So it was so difficult to deal with this lack of ability to make the best use of the theory of perceptive vision. So the manipulation was all done by the software, all done by the coding. And as we know, we use the Quartz software to write the program for the Altera board DE2-115. And to illustrate it simply, we have 9 main modules and 1 top-level module. I will talk about 4 modules, which I mean. The first module is the clock generator. The clock generator that generates the clock for 1 second. It takes a 50 million hertz from 50 million hertz clock from the Altera, and it takes the 50 million hertz from 50 megahertz clock from the Altera, and it outputs the 1 hertz clock. It is done simply by setting a counter, and when this counter reaches 25 million, the signal, the present signal will reverse itself. So when I reach 25 million at a high signal, it will be a low signal, and vice versa. The other module is a clock generator. The The other module is a clock generator to generate the clock for the 1 degree cycle of the fan. This module simply takes also the 50 megahertz clock and outputs this clock. We did our math and we used some equations to specify the count, to specify when I will reverse the signal. So we took the 25 million count of the module which generates the 1 second clock, and we took this 25 million count and we divided over 20.3, which is the number of cycles per second. Then we divided over 360, which is the full angle of the circle of the cycle. And when the counter reaches this specific number, I reverse the signal, and else it will complete counting. The third module is the 60 counter, which simply counts from 0 up to 59 by checking the units and the tens. When the units reaches 9, I will check the tens. If it is 5, I will reset the 2 segments to make it 2 zeros, and else I will reset only the units and complete counting or complete increasing the tens. The last module is the 7-segment decoder. The 7-segment decoder is simply a module that takes the number and display every bit on the corresponding segment of the 7-segment to show the output that we need.
Now I will talk about the rest of the modules. The first one, which is called 24 counter, that counts the 24 hours. The second one is the basic one in our code, which is called hours, minutes, seconds. That takes the hours, minutes, seconds, segments as inputs and return to us the hours, minutes, and seconds as one by one digit at its location on the spinning wing. In this module, we use the clock 3456 as one cycle. It calculated as a clock that coming from the Altera over the number of 20 radians per second according to our motor velocity over the 360, which is the corresponding for every 1 degree in the rotations. Also, we use the counter for setting the distance between the digits. The second module, which is called Eclipse, this is the module that corresponding for setting the 7 segments, showing the team name on the spinning wing. This module uses the same clock that mentioned in the previous module. Now with the change module, which is concerning about controlling the output, either to show the clock or the word Eclipse by giving a signal to a button on the Altera to activate one of the two outputs. Our top level module is Eclipse clock, which relates all the previous modules together to show the required output and takes the clock as an input.